Okay, I think we're live. Yes. So, it is week 2 of statistics. We have last week covered mean and median measures of center. So when you have statistics, you have a lot of values, a lot of information, often numbers, and measures of center are ways of finding the middle of the data. So that's just a little review. We've moved on. Now we're covering measures of variability. Now, will we still need to use mean and median in this week's lesson? Well, perhaps some surprises are in store for us. Maybe they'll be more useful than we thought. But what I have so far to introduce the idea of measures of variability, how much does the data vary? So when you think of the data having a middle, well, how far does it stretch on either side of that middle? That's a good way of describing what a measure of variability is. So we're going to be looking at 3 different measures of variability this week. And to start with, I have 2 sets of data. And I'm not going to give too much information about how I collected this data or what this data is really about, but it has to do with number of slices of pizza eaten by people. And over on this side, we have weekends. So what does that mean? I'll explain later. But someone ate 5 slices of pizza, someone ate 3 slices of pizza, and it goes on. You might notice some patterns over here. And how many values do I have in my data set? I have 12. The sample size is 12. That's useful, so I want it showing. And then we have another set of data that's not very different at all, right? We have number of slices of pizza eaten by a person, a certain number of people, but this time it's on weekends. And the numbers, there are more. The sample size is 18, the number of data points is 18. But there's also some other different looking patterns in here, which again, I will explain later. So what we're going to do is we're going to look at measures of variability. Well, we're going to look mostly at the first measure of variability, which is range, for both of these sets of data. But what else can we do with this data? Well, we know from last week that we can find the mean and the median of the data, and it's not going to hurt. With statistics, even if you're doing a question that has to do with something like range, something like variability, it doesn't hurt to understand as much as you can about the data. So it's not going to hurt for me to reveal the mean and the median for both of these sets of data. So this is the weekend side. The sample size is 18. The mean is, where'd it go? 3.17. Now I did calculate this earlier, and it's possible that I have made mistakes. I always do in these lessons, and now that I'm doing these hour-long videos, there's not enough time for me to find a mistake and correct it during the video, so the students are welcome to find my mistakes and tell me about them in their comments. What is the median of this data? The median is 3. And of course, you know that this data is not ordered from least to greatest, but to find the median, I had to reorder it from least to greatest. That helped me to find the median being 3. That's weekends. Now I'll give the mean and the median for the weekday pizza data. The mean, let me make sure that I'm not going over, I think I'm good. The mean of this weekday pizza data is 4.25. And the median is 4. Okay. The range, what's the range? The range is the distance between the least value and the greatest value. You find the greatest value and you subtract the least value, and the difference that you get, the answer to that subtraction, is the range. So range is actually a simple little thing to find. Well, let's do this. Pizza weekends. The smallest data point that I find here is this one, 0.5. And the largest is 6, which happened more than once. But to find the range, all I'm going to do is take that largest and subtract the smallest. Oh, that's a little messy. And I get a range of 5.5. So the difference between the smallest amount of pizza that a person ate, half a slice, and the largest amount that someone ate, 6 slices, is 5.5 slices. And that tells us something about how much our data varies around those central points that we call the mean and the median. And it's a different statistic. It's a different statistical measure that tells us just yet a little bit more about our data. And that's the point of it. Okay, the range of the weekday pizza data, the greatest value again is 6, which happened 3 times here, but the least value is 3. So the range is 3. So there is less variability in the number of slices of pizza eaten in this weekday data than there is in the weekend data, where there's a much greater amount of variability. That's kind of interesting. So it tells us something about our data, something more than we would have known if all we looked at were the measures of central, the mean and the median. Okay. What I knew ahead of time was the meaning of this data. When I collected the data, what I did was, in the last 6 times that my wife and I ordered pizza on weekdays, when it was only the 2 of us eating the pizza, I recorded how many slices I ate and how many slices she ate. I'm the one who has these big numbers, so that's me eating 5 slices, 6 slices, 5, 5, 6, 6. And you start to understand that Doug really likes pizza, and so you wouldn't be surprised if you knew me that I can eat quite a few slices of pizza. My wife tends to eat 3 slices, and in fact every single time she had 3 slices. So that gives us a little bit more of the meaning of how the data was collected. When we know that that's how I collected the data, we're not too surprised to see the values that we found for the measures of center and for the measure of variability. The range between the 3 that she always ate and the 6 that I sometimes eat is 3. So what's the difference over here? Weekends, how would it be different on weekends? Well, the clue is that this also represents 6 times that we ordered pizza, the last 6 times we ordered pizza on the weekend. But what happens on weekends is very often we have a grandchild sleep over. And when grandchildren sleep over, that's often a reason for celebration. And how does Doug like to celebrate? He likes to order pizza. So we often have pizza when we have a grandchild sleep over. And some of these grandchildren are pretty small. So then you start to see the pattern as really the same pattern, but with the difference that you see the 5, which sounds like Doug, and the 3, which sounds like Doug's wife, Bunny. But then you get a really small amount, like 0.5, which is from the youngest grandson, who has just turned 3. And then 6 is Doug, 3 is Bunny, 1 is a different grandchild who's a little older. Doug, Bunny, grandchild. Okay, the oldest grandchild is 8. Oh, look, 1 week Doug only had 5 and Bunny only had 2. I don't know if Bunny was not feeling well that day, or maybe it's just that we had a large lunch. And that's another thing that can affect the data. If we have a large breakfast or a large lunch, especially the breakfast, this happens. That on weekdays we never have a large breakfast. It's just a piece of toast or a tub of yogurt or something like that. But on weekends we often have a cooked breakfast. And that makes you less hungry, and then when supper time comes and the pizza arrives, you're not going to eat as much. So that might explain why Bunny only had 2 slices that time. And then of course, what I did was each set of 3 data points, the way I happened to write them down, is Doug followed by Bunny followed by grandchild, and the grandchild is the one that's varying a little bit more because it's different grandchildren on the different weekends. Some of them are bigger than others. All of a sudden, these patterns make a little bit more sense. But the point of that is to discuss how with statistics, 2 things can happen. You can compile statistics, you can gather the data the way I did, already understanding a lot about the data because you're the one doing the experiment, and you're understanding, as you record the numbers, you're often understanding why you're getting the numbers that you're getting. I knew that there are grandchildren involved on the weekends and not on the weekdays, so I wasn't surprised to get these really small amounts like 0.5 and 1 on weekends, and to not get them on weekends. I wasn't surprised by any of the values I got because I'm the one who collected the data. But it's still useful to show the statistics because I may not be the only person to look at this data. I may not be the only person to look at this experiment. And so other people who don't necessarily know the background of how the data was collected can still learn a lot by looking at these values. And then they can come up with hypotheses. They can come up with theories as to why the data is different on weekends than it is on weekdays. We are really showing how, with math, the topic of statistics really has a lot of overlap with the world of science. Because science is a place where you use math with a purpose. And statistics is a type of math that is very frequently used by scientists so that they can find the meaning in the data they collect. What else can happen, of course, is someone could see the results and see the statistical values without knowing any of that background information, and they can come up with their hypothesis, their theory as to why it happened. Would someone see this data and notice the different pattern in the numbers and look at the difference in range and mean and median and be able to understand that it has something to do with whether there's a grandchild sleeping over or not? They might not be able to figure that out, but we're giving them some ammunition to work with, so giving them some values to work with to try to figure things like that out. And scientists do a lot of that too. Okay, so what other pattern can we notice? That on weekdays, we have larger mean and median than we do on weekends, but we have a smaller range than we do on weekends. So that it's interesting that the patterns can be different for the measure of center than they are for the measure of variability. So that's quite a long description. And really all I got into that's from this week's lesson is the idea of range and how we use it, but within context. And notice how useful it was for me to look at the mean and the median, the measures of center that we covered last week. Just because they're from last week's lesson doesn't mean that they're not involved in this week's lesson, and we will see that happening more than once. Okay, so I finished with the pizza experiment, the pizza example. I'm going to do some erasing. We're doing quite well for time. That took 10 minutes, but it is the introductory topic. Now we're going to practice finding range, so I'm going to try to do a few quicker examples. Brand new microfiber cloth for today's lesson. I don't need any of this anymore, so I'm erasing it all. And if anyone's wondering where my beautiful assistant Mocha is, she's upstairs. And the reason she's upstairs is because we have a grandchild who slept over. And it's not the weekend, but we had a grandchild slept over because we are babysitting. And that means there's a lot of activity going on upstairs and around the swimming pool. And I know that if I force my beautiful assistant to be down here like I normally do while I'm teaching, she'll be at the door whenever there's any noises up there, and she'll be sniffing and whining, wanting to go up there to see what it's all about. So I figured I'd just let her off the hook and she gets the day off. Okay, that's erased. Now, I'm going to give some data. I want to give some data in a way that's a little quicker. So I'm just going to say this is quiz grades. Quiz grades. You can always use quiz grades for an example in statistics. Now, quiz grades can mean two things. I have, how many values do I have? My sample size is 9. So there are 9 quiz grades that I'm going to write down. And I'll write them already ranked from least to greatest. 12, another 12, 13, 14, 16, 2 17s, 18 and 20. Is it fitting? Am I writing large enough? Yes. Okay. So 9 values. I'll say my sample size n equals 9 because that keeps on coming in handy when we're doing these analyses. Now it could mean two different things. This could be a small group of 9 students and all of the results, and this is graded out of 20, so someone got a perfect grade. It could be 9 different students and their grades, or it could be one student who had 9 quizzes to do that were all out of 20 over, say, a 9-week period, and it could be all the grades that student gotten, but not necessarily in the order that they happen. They're listed in order from least to greatest. And there's a reason for that. Now, of course, we can find the range. Well, we already found a range, and we know how, and it's not the longest mathematical trick to do. The range is the greatest minus the least. The greatest value is the 20. The least is the 12. The range is 8. But then we also can look at the interquartile range. Interquartile range is a second measure of variability that I'm covering in this week's lesson. It's also pretty fast to calculate, but it involves using median. So there's median coming back from last week's lesson, and it becomes useful again because you will always find the median as a step when you're going to find the interquartile range. I will write interquartile range as IQR. Interquartile range, if I want to give it a definition, is the difference between the median of the top half of the data and the median of the bottom half of the data. Well, that just sounds crazy. That just sounds weird because I'm just pulling that right out of nowhere. But these differences, these values that we need to calculate that difference, all involve finding medians. And I know that the students know how to find median because we did quite a few examples practicing it last week. So, small review, the median of this data is easy to find because there's only 9 data points, and it's an odd number of data points. So when there's an odd number, there is just one value that's right in the middle, and it's that 16. When it's a small amount, we can find this quickly because we can quickly realize, well, if I circle that 16, I have 4 values to the left of it and 4 values to the right of it. But because this is median, the data has to be ordered from least to greatest for this to work. So that's why I did it. Now, we have to find the median of the first half and the median of the second half. So that's new. We didn't do that last week, but it's still finding a median. So it's not very different. When we look at the left half of the data, because we have an odd number and there's an actual median, an actual value right in the middle, we don't count that as part of the left half or the right half. The median of the left half, therefore, is going to be the average of these two middle values. And the average of 12 and 13 is 12.5. Over here, same thing happens. We don't count this on the right half, we count these 4 values. The median is going to be the average of these two values, the 17 and the 18, and therefore is 17.5. So we already know how to find median. What happened is we found median 3 times. And you have to get used to it because it is still new that you're finding 3 medians. Okay, median of the whole group, median of the left side, median of the right side, and different patterns can happen. You have to practice so you can see the different things that can happen. But they don't get very different. And the method of finding the median is really the same thing that we did last week. So the interquartile range is the difference between those two values. So we take the larger of those, which is the 17.5, and we subtract the smaller, which is the 12.5, and the difference is 5. The interquartile range is 5. That's interesting. So it's another measure of variability. It's another measure of how the data spreads out on either side of that central point. And the range is all of the values in the data set, how much they stretch out around that median point, middle point. But the interquartile range doesn't go all the way to the outside edge of the full data set. That's kind of interesting. What's useful about it? Well, now we have 2 different measures of variability that we can find. And what happens to these, and which one we want to look at when we're trying to draw conclusions from the data, will depend on the type of numbers we have. So this is just the first example where I'm doing this. We'll see how this can be a little different in different questions. Okay, so I'm finished with that example. That's good. Okay, do I want to erase it? I'm going to take a look. I'm going to have to erase it because I won't have room otherwise. How am I doing for time? Pretty good. And remember that, no, don't remember that. Remember this. Okay, my next example, a bunch of kids went bowling and I put down their scores. Now, why did I choose bowling for this example? Because I went bowling just a week and a half ago, and it was the first time I've been bowling in 30 years. So you might not be surprised to find out that I didn't get a very good score. But when you go bowling, you don't necessarily do it to get a really good score. It's fun for everyone. It's fun for beginners. It's fun for people of all ages. And when I went bowling, I brought my mother with me, and we weren't really sure if my mother could do the bowling. But in the end, she could. And what I would do is I would help her get up to the line that you throw the ball from, and then she would use her cane. And then I'd take her cane and give her the bowling ball. And when she needed the second ball, I would hand it to her so she didn't have to walk back and forth. Her throwing style was a little crazy because she wasn't trying very hard to bend down, so the ball was coming out of her hand pretty high and hitting pretty hard. But she did okay. Now, when you have people bowling, it's interesting, it's a good sport because you don't really compete against the other people. You can, but you can also just compete against yourself. You try to get a good score. So I have a bunch of bowling scores. I'm going to write them down. I don't even know what the sample size is right now. I'll have to give that to you. Okay, all erased. Bowling scores. And of course, the meaning of bowling scores depends on the type of bowling it is. There's 10-pin bowling and 5-pin bowling. I don't even know what type of bowling this was, so the meaning of what's a good score and what's a bad score isn't really that apparent to me, but it doesn't necessarily matter because we just want to practice finding the range and the interquartile range. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It happens to be 13 values. I'll write them down, 7, 9. And yes, I can see these are not very high scores for bowling. 40, 42, 44, 47, 51, 54, 60, 62, 68, 92, and 133. Okay, so a couple of these people are quite a bit better at bowling than most of the others, and a couple of these people are really not all that strong at bowling. Boy, does that line of numbers ever look crooked on the camera, but it doesn't look crooked to me. Interesting, I have to tilt my camera differently. But it will do, so long as you can read them. Okay, so the range, I happen to have already listed them from least to greatest. This is helpful. The range is very fast to find, therefore. 133 is the largest number and 7 is the smallest, so the range is 126. The difference between 133 and 7. Yes, okay. The interquartile range, well, we have a little bit of work to do finding medians before we can find that. There are 13 values, and that's an odd number, so there is a middle value. There are going to be 6 values to the left of it and 6 values to the right of it. 1, 2, 3, 4, 5, 6. That means 51 should be my median. 1, 2, 3, double check. 4, 5, 6. Yes, it is. So the median is 51. And then the median of the left half, the median of the right half. We count the values and we realize, oh, again, we're not going to count this as one of the left half or one of the right half values. There are 6 values, which means there are 2 middle values. It's easy to find them, and the median of those is the average of those 2 values is 41. And then we do the same thing over here. There are 6 values. The 2 middle ones are the 62 and the 68, and the average of those, the mean of those is 65. So it's that quick. To find median becomes that quick, although it takes longer to do when you have a larger amount of data. But when you have a small amount of data, finding 3 medians, finding everything that you need to find the interquartile range, is really that fast. So it is going to be 65 minus 41. The interquartile range is 24. Okay, in my previous data about the quiz scores, there wasn't a very big difference between the range of 8 and the interquartile range of 5. But this time, there is a very big difference between the range of 126 and the interquartile range of 24. Why? Because we had a couple of people who had much lower scores than everyone else, and we also happened to have a couple of people who had much higher scores than everyone else. That doesn't always happen, but it can happen. And it helps to illustrate why we want more than one measure of variability. Why range isn't just always going to be enough. Because the range is telling us something, and the interquartile range is telling us more detail. So a very large range might tell you, well, there's a huge amount of variability between the scores of all these people who went bowling. But the truth is, that isn't really that true. There are a lot of people who got scores between 42 and 68, which are not really that far apart. And then there's only a few people who are outside of that. So therefore, the interquartile range might be something that's a little bit more trustworthy when we're trying to figure out, okay, what's really going on with these bowling scores? What's really going on with these bowling scores is around the median of 51, there's an interquartile range of only about 24 values on either side of 51. Most people got scores that were not very different from 51 minus 24 or 51 plus 24. So these values can be seen as a little bit misleading depending on what it is that you're trying to find out from the data. Which one tells us more? I think with this data, the interquartile range tells us more. With the previous data with the quiz scores, neither of them told us more. That depends on the data. So that's good for that example. Now I'm going to do 3 more examples, but this time I'm not going to make it quiz scores. I'm not going to make it bowling scores. I'm not going to give a meaning to it at all. I'm just going to give a bunch of numbers, and we're going to practice finding the range, because only if we're going to practice finding the range first, and then we're going to practice some interquartile range later, because practicing with only 2 examples, that's not enough. So, some data. Here's some data, and just called it data set A, so they have no meaning behind these numbers. 3, 17, 82, 84, 88, 905. Now right now we're only looking at range. We're just practicing finding the range, so we're not doing the interquartile range, so we're not using median. We're just doing greatest value minus least value. 905 is the greatest value minus 3. I have a range of 902, a very wide range. Why? Because we had some small numbers and we had this one very big number. That can happen. Okay, a second set of data. I won't erase this one yet. Data set B, we have a 20, 40, 12. Oh, these were given in increasing order. This one, it's not given in increasing order. 20, 40, 12, and then we have an 80, 51, 16, 13, 79, and 77. Okay, so to find the range, it's easier if the data is ordered from least to greatest, but unlike the median, where you really want to reorder data like this so that it is from least to greatest, with the range usually you're able to find the largest value and the smallest value without having to reorder it. So I'm looking around and looking for that largest value, and I realize it's the 80. From that I am subtracting the smallest value, and I look for it and I see the 13, but I see a 12. It's going to be the 12, and therefore the range of this data is 68. Double checking, yes, that agrees with the calculation I did before. Okay, so not too bad. It is quite quick to find the range. Even when the data is not given in increasing order, it's not too hard to find that biggest value and that smallest value so that you get the correct range. I will erase and I'll do one more example. Now this example, the values are a little more jumbled up. And I admit, I kind of did that on purpose. Okay, so data set C, I have 5, 10, 15, 20, 25, 25 values, but the way I'm arranging them, 43, 57, make sure that looks like a 7, 18, 41, 32, 42, 9, 61, 74, 80, 88, 101, 49, 8, and 74, 92, 60, 102, 41, and 75. Finally, 75, 77, 80, 84, and 16. Now I have to apologize for having so many values. For students who are trying to take notes, the students could be trying to write down all of these values, and sometimes I talk really fast and I go through the problem and I erase, and the students might not have time to write them all down. I am concerned with having time myself, that I don't want to use up the entire hour of the lesson just writing down numbers, but I also have to remember that the students might also be writing down the numbers. Now, of course, you can, if you're watching a video, you can pause it, you can go back and you find the numbers, but if you don't want to interrupt yourself as you're going through a video and you want that flow, that can be a little bit inconvenient. What I am going to do for the third and fourth lessons of statistics in the next 2 weeks is I'm going to use data from a homework pack so that the students can already have the data and not have to copy it down. And I'm especially finding that it's important to do that because next week we're going to start looking at graphs. And it can take a little bit more time to construct a graph. So that's the plan. But this bunch of data, there have to be a lot because I wanted to make the point of, well, what happens when you have a lot of data? Is it going to cause you to make a mistake? That's the question that I'm dealing with this little example. We're looking for that greatest value and that least value, and these values were not listed in increasing order. If we're not going to relist it in increasing order, which would take some time, how can we make sure that we find the right values? Really, we have to be careful. So there is one trick though with data like this. When we're looking for that least value, I'm going to make room for my range calculation. Oops, range. I'll do the calculation here. I'll look at the least value first. It just so happens that there are only two one-digit numbers in this data, the 9 and the 8. So the fact that most of the numbers have 2 digits, but I can find quickly those ones with 1 digit kind of helps, makes it a little easier. So 9 and 8, the smaller one is 8. I am going to be subtracting an 8 when I figure out my range. But the largest value, well, the same sort of thing is happening because most of the numbers have 2 digits, but a couple of them have 3 digits. And if we're careful, we realize, oh, there's 101, there's 102. 102 is bigger, so I'm able to find the value I need. 102 minus 8 is going to be 94. Is it 94? Yes, it is 94. He double checks, not wanting to make a mistake. So I was able to do it just barely. Now, what if we didn't have these two one-digit numbers and we didn't have the two three-digit numbers? What if those 4 numbers were not there, but instead there were 4 other 2-digit numbers? Well, that makes it a little bit more difficult. You get to a point where you have to decide when it's worth the trouble to reorder the values from least to greatest. Carefully crossing them off as you go, making sure that the total is the same after you reordered it. This time I had 25 to start with. If I'm reordering it, I want to make sure there are 25 values after the reordering. If there are 24 or 26, I made a mistake and I have to find it. If all of them were between 10 and 99, we wouldn't have any single digits or triple digit numbers to work with, and we'd have to be more careful. That's the point of that question. And that is my last question where all I'm finding is the range. I've now done 5 examples of range, and we're going to move on and do some more examples of interquartile range. Aha. Okay, and I'm watching to see where I'm at for time. I think I'm doing okay for time. Now, interquartile range, the good thing is that I have already introduced it, and in fact I've done 2 examples, so I just want to do several more examples of interquartile range the way I did with range. This one looks like it's a little cleaner. And I'm not going to give any more very large data sets like this one, where the sample size was 25. That's a little much with all this writing. So these ones, where's my page? There it is. I'm going to try 4 different sample sizes, but they're going to be very close to each other. I'm going to try sample sizes of 9, 10, 11, and 12. Why? Because I want to see the patterns of what happens when you find all these medians, when you have different numbers of values. It's not just the thing about odd and even. And we already know there's a little difference finding median from a group of an odd number of numbers and an even number of numbers. But that's not the only pattern that we can notice. So if the sample size is 9, and I'm not giving meaning to this data, it's not polling scores or quiz scores or anything like that, it's just a bunch of numbers. Let's try these values, 12, 14, 15, excuse me, 18, 20, 21, 26, 28, and 32. Give me a little bit more chalk. 26, 28, 32. Okay, so there are 9 values there. Yes, there are. That means finding the median is very fast. The 20 is the median. There are 4 to the left of it, 4 to the right of it. So I'll write just the 20. We know that's the median. The left side, we're counting these 4 values. So the median is going to be the average of these 2 middle values, which is going to be 14.5. And there's that mean thing coming in handy again. And the right side, the same thing happens. The average of these 2 values is 27. Notice how we got a decimal over here, but it doesn't mean you always have to have a decimal when this happens. It depends on the values that you have. So we are finding our interquartile range, and that's going to be 27 minus 14.5, which is 12.5, I think. I never actually wrote down the answer. Yep. So 12.5 is the interquartile range for this data. And we see the pattern that happened when we had a sample size of 9. Now without erasing, underneath I'm going to do the sample size of 10. It would be nice to fit all 4 of these examples, 9, 10, 11, and 12, but I'm not going to be writing down there. So I'll erase after the second of these, and then I'll put up the data for the third and fourth examples together like this. Okay, sample size of 10. What values do I happen to have this time? 30, 31, 33, 35. 38, 40, 42. 46, 47, 48. Okay, so it's an even number of values, and that means that there's not a single middle value. There are 2 middle values, which are still quite easy to find because we still have quite a small data set, only 10. So these 2 are our 2 middle values, and the median is the average of those 2, which is going to be 39. The average of 38 and 40 is 39. Now, the left side, right side thing, what we'll do is we will count the 38 as part of the left side and count the 40 as part of the right side, because it just makes sense that we can do that. Therefore, the left side has an odd number of values, and that means it has a middle value, and the median of the left side is 33. The right side has an odd number of values, and its middle value is the 46. So our interquartile range is going to be 46 minus 33, which is 13. Fast to find the interquartile range. It's always fast to find the answer once you've done all this work. But the point of these examples is the patterns that are happening. When I had a sample size of 9, I had a middle value for the median, but then I had to do the average thing for the 2 others. I can write over here, middle, then 2 averages. That's the pattern that happened with a sample size of 9. But with here, there was no middle value. I had to do an average. And then on the left side and the right side, there were middle values. Then 2 middles. Okay, so it's a little bit messy to look at. But one thing that I can tell you is that every time you have a sample size of 9, this is going to happen. You're going to have a middle value, but then you're going to have to use the average thing to find the median of the left half and the median of the right half. The median of the lower half of the data and the median of the upper, larger half of the data. And every time you have a sample size of 10, this is going to happen. You're going to have to find an average for the median, but then you're going to find those 2 left half, right half medians, you're going to have middle values. It always happens when there's a sample size of 10. Well, what happens if there's a sample size of 11 or a sample size of 12? Let's answer that question by doing 2 more examples where we have those sample sizes. I'm going to erase the data and the interquartile ranges, but I'm not going to erase those 2 sample sizes and the pattern that happened with them. So we're going to go to a 3rd sample size, and I'll write it over here, and it's going to be sample size of 11. Does that fit? It fits easily. Okay, so writing the data with sample size of 11. And notice how I keep juggling the numbers. We had a whole lot of numbers that were sort of in the teens and the 20s with the first set, and then the 30s and the 40s with the separate set. The point is that it doesn't matter if you have little teeny numbers, very big numbers, 5-digit numbers, decimal, little decimal numbers, fractions. You can do statistics with all of it. You can find the measures of variability with all of it. Okay, so this set of data will be faster to write though because it has some single-digit numbers. 4, 6, 7, 8, 10. 4, 6, 7, 8, 10, and then 11, 13, 18. I need 3 more, don't I? 20, 22, 27. More chalk, please. I'm running out of this piece of chalk. Okay, so 11, it's an odd number. It means that there is a middle value. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The sixth value is the middle value. Notice how as the sample size gets bigger, I slow down a little bit when I'm figuring out what the middle value is, because the larger the sample size, the more difficult it is to make sure that you get that right. But there are 5 values to the left of it, 5 values to the right of it, so I feel good about this. So my median is 11. Then the left side, I don't count that on the left side or the right side, so the left side happens to be an odd number of values again, and the median is very fast to find, and it's 7. And the same thing happens over here, so the median of the right side is 20. Finding the interquartile range is really quick with this example. 20 minus 7 is 13. The interquartile range is 13. I found it. I feel quite confident in it. What's the pattern though? Here we had, for a sample size of 9, middle, then 2 averages. For 10, we had average, then 2 middles. But for 11, all 3 of them were middle values. All 3 are middles. Well, I want to include my sample size in that little balloon. So I'll do some creative erasing. Okay, well that's interesting. So I guess students probably will really love having sample size of 11 in their examples when they're doing their homework or any practice, because it's going to be so quick to find all those medians. All of the values are actual data points. And it's the pattern that happens when you have 11. Interesting how now we've seen 3 different things that happen. So it's not just 2 things that happen, like when you have odd or even. Depending on how many are on the left side of that first median, how many on the right side, you get different patterns. You end up with more different things that can happen. Last example for interquartile range. I'm going to have to write it a bit lower. I used a lot of space for this one. I have a bunch of numbers. They're bigger numbers, but they have a lot of zeros in them. 50, 80, 90. Here, I'll put a little squiggly line between them so it doesn't look too cluttered. 50, 80, 90, 100, 110, 140. Sample size is going to be 12. Haha, get ahead on that. 150, 160, 170. Have to fit 3 more. 175, 180, 190. 175, 180, 190. I almost ran into my sample size there. And that's it for that piece of chalk. Okay, getting a brand new piece of chalk. How many do we have? We have 12. The sample size is 12. Let's make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, sample size of 12. We are looking for another pattern, and I'm telling you right now, it's the last pattern. Okay, it's even. So there are 2 middle values. These are going to be the 2 middle values, right? Did I do that correctly? 1, 2, 3, 4, 5 to the left, 5 to the right. Yes, I found the 2 middle values. The average of 140 and 150 is going to be 145. Then on the left side, we count the 140 on the left side. So it's 2 middle values again. We have 6 on the left side, 6 on the right side. So we have to do another average, and we're going to have 95. And on the right side, same thing happens. We have 2 middle values, so the average is going to be 177.5. Yeah, 175 and 180, add them together, divide by 2, you get 177.5. So my interquartile range, really, once you've done the work, the interquartile range is still always just as easy to find. We take that median of the right side, we subtract the median from the left side. I didn't write down the answer ahead of time, so I have to make sure not to make a mistake. It's going to be 77.5 plus 5, 82.5. And yes, if I make a mistake, please correct it in the comments so that I know about it afterwards at least. So what happened here? All 3 were averages. You must be wondering, does this go on forever? In a way. Does it go on forever that you keep on finding different patterns every time you change the sample size by increasing it by 1, 9, 10, 11, 12? Middle then two averages. Average then two middles. All three are middles. All three are averages. I guess I should put the word R in there. There. No, it doesn't go on forever, because what happens is when we move on to the next sample size up, which would be an n equals 13, this happens again. And for 14, this will happen again. And for 15, the three middles will happen again. 16, this will happen again. 17 will be like this. So now we've seen all of the four patterns of whether you're finding a true middle value or the average of two middle values. As you're doing all of these medians, that's a lot of medians. We have found so many medians in today's lesson that you would think was last week's lesson, which was about median. But remember, I always said at the beginning of this lesson that median might come back and be helpful. Well, you can see median is extremely helpful when you're finding interquartile range. What's also helpful is to do a lot of practice so that you see these patterns, because once you realize all the patterns that can happen, they can't confuse you anymore. You realize why this happens sometimes and this happens other times. And then when you're given a new data set to practice with or to answer a question about, you're not surprised by the pattern being different than the last time, and you can handle it no matter what they throw at you. That is the point of me doing these four examples. How am I doing for time? I have about 15 minutes left, and that's good because I need it all for mean. Where did I put it? Mean absolute deviation, which is the third and last measure of variability that I am covering in this week's lesson. Mean absolute deviation. Mean? Why would I be mentioning mean? Because it's not only median that comes back and is useful in this week's lesson, but mean, which we also covered last week, comes back and is useful right now as we do mean absolute deviation. Let's look at that. I'm going to erase all this stuff now. And I'm going to put a heading for the last topic in today's lesson, mean absolute deviation. So mean comes back and is useful. And mean absolute deviation can be abbreviated as M.A.D. much like interquartile range can be abbreviated as IQR. M.A.D. Mean and M.A.D. That rings a bell that's coming back at me from my childhood. There is a TV show I watched that was made before I was born, so yeah, that's a really old TV show. And in the TV show, one of the characters is told to go to a place where there are people who don't know who he is, and to be mean and mad. Can't remember why. But I found it funny when I watched it happen, because when the character arrived at the place, he walked in and he said, "I'm mean and I'm mad." And I like that. I'm mean and I'm mad because we use mean, which we learned last week, as part of the process of finding the mean absolute deviation, which is abbreviated M.A.D. So I'm mean and I'm mad might be something from an old TV show, but it also is something that helps me remember everything about the rest of today's lesson. Mean absolute deviation. Mean, M.A.D. And if anyone wants to in the comments, they can try to identify the TV series I'm talking about and maybe even identify the particular episode. That's a challenge. And Googling it might not help because I tried Googling it before I did this lesson and I didn't actually find it. Okay, so I don't remember which exact episode it was. Interesting. Little trivia question there. What if we have a bunch of data, and I'm going to put a really simple bunch of data up on the chalkboard. How about 10, 20, 30, 40, 50, 60, and 70? So there are 7 values, and of course we know how to find the mean, we know how to find the median, we know how to find the range, we know how to find the interquartile range, but now we want to learn how to find the mean absolute deviation. Well, the first step, you won't be surprised, is to find the mean. The mean is 40. 10 plus 20 is 30, plus 30 is 60, plus 40 is 100, plus 50 is 150, plus 60 is 210, plus 70 is 280. There are 7 values. 280 divided by 7 is 40. Yes, I double checked. I did it in my head. I'm being a bit of a show-off, but I also knew that I was going to get a mean of 40 because I conveniently created a bunch of data where I'd be able to figure out what the mean was as I created the data. Okay, so the mean is 40. How is that helpful to us? Okay, what we want to look at when we're learning mean absolute deviation is how far do each of these values spread away from that mean of 40? Oh, well, 30 is 10 away from 40. And 20 is 20 away from 40. So I guess what I'm doing is I'm saying 40 minus 30 is 10. 40 minus 20 is 10. 20, sorry, 40 minus 20 is 20. So that's easy to do, especially because I give these nice, easy to work with round numbers. 10 clearly is going to be 30 away from 40. 50 is 10 away, 60 is 20 away, 70 is 30 away. We can see how far each of these values is from 40. So I'm going to write how far they are away. 30 is 10 away from 40. 20 is 20 away from 40. 10 is 30 away. 50 is 10 away. 60 is 20 away. And 70 is 30 away. Well, the mean absolute deviation is the mean of these deviations. The mean absolute deviation is the average of these numbers. The average of those distances, each data point is from the mean. So if I average these, I am going to get an average of 20. And yes, I can do that in my head, but I will also show it. 10 plus 20 plus 30 plus 10 plus 20 plus 30, all divided by, how many values did we have? 6. Oh, I'm missing one. 40 is 0 away from 40. I missed 1. So I'm not dividing by 6, I'm dividing by 7. How far are each of these values from 40? It was kind of easy to make the mistake I just about made there. This is 30 away, that's 20 away, that's 10 away. This is 0 away. This 40 is not far from, it's from 40. It just so happens the mean happens to be equal to one of the data points, and that's why I almost made that mistake. So it turns out there are 7 data points, so I need 7 values here. I need 7 values there. I have to add that 0. It's included. So when I divide, I'm dividing by 7. My mean absolute deviation is 20 because when we add these 7 numbers together and divide by 7, we should get 20. Let me double check it. 0 plus 10 plus 20 is 30, 60, 70, 80, 90, 120. Oops. Okay, I made a mistake. I did make a mistake. And that is because when I forgot to put that 0 in, I forgot when I made my notes. Okay, so it's not a horrible mistake because it's very easy to fix. I just have to change my answer. 120 divided by 7 is not 20. I was dividing it by 6 by accident. I will use my calculator because I am going to get a decimal. 120 divided by 7, it's a mean absolute deviation of 17.1. Nearly gave the students something to catch me out and tell me about in the comments. But I'm certain that I must have made a mistake somewhere in this week's lesson because since I've been doing these hour-long videos, I've made a mistake at least once every week. I only have 7 minutes left. I want to do some more examples of mean absolute deviation. This was a little bit of a procedure with this whole drawing of arrows thing, and it's actually part of the reason I made the mistake, but this isn't the procedure I recommend anyway. This is not how we normally do it. It's just a way of introducing the topic. So I will leave the mean absolute deviation and its abbreviation labels up there, and I'm going to put up some more data, and we're going to find another mean absolute deviation. What do I have here? Okay, this time I'm going to give the data in a table. We have values of 14, 16, 17, and 19. No, that's a 9. It's a little messy, sorry. 21, 22, 24, and 35. Oops, why am I drawing a line there? I need a 35, then I put a line. There. So these are my values. Now I made up values, I don't have a meaning for these. Let's call them, I don't know, some type of score for some type of sport. All right, so you get these scores in this sport where you can have scores like 14 and 35. We can find the range very easily. 35 minus 14 is 21. The range is 21. We could find the interquartile range if we wanted to. We can find the mean. We can find the median. We have to find the mean because finding the mean absolute deviation involves knowing the mean. The total of these values is 168. And when I divide that by how many values there are, and there were 8 of them, I get a mean of 21. The mean is 21. I'll write mean. We have not gotten to the M.A.D yet. We have not gotten to the mean absolute deviation yet. The first step is always to find the mean. Now, what's useful is to record all those differences the values are from the mean by adding a column to your table. So I'm going to make a little topic, little labels here. And I'll call this just data. And here I'm writing distance from mean, which is really a long label. Distance from mean. Better make this line longer. There. So the distance from the mean, I don't need this wide a column for the numbers I'm about to write. I have a very big wide column. The distance between 14 and 21, well, we just have to say 21 minus 14. 21 minus 14 is 7. Notice how I started with the mean and subtracted the data point. But I won't always do that. The distance between 16 and 21 is 5. 21 minus 16 is 5. Difference between 21 and 17 is 4. Difference between 21 and 19 is 2. All of those were easy to find by taking the mean and subtracting the data point. The distance between 21 and 21 is 0. I have to include that. But now the distance between 22 and 21, I don't want to say 21 minus 22. I don't want to put the larger number after the smaller number when I subtract. So I'll just do it backwards. 22 minus 21 is 1. The difference between 22 and 21 is 1. It makes sense. The difference between 24 and 21 is 3. And the difference between 35 and 21 is 14. Now I know all of my deviations, all of my distances from the mean for all 8 of the data points, and I can find the average of those, which will give me my mean absolute deviation. But first I need to know their total. 14 plus 3 is 17, plus 1 is 18, plus 0 is still 18, plus 20 is 20, plus 4 is 24, plus 5 is 29, plus 7 is 36. That 36, when I divide it by how many data points I had, which is 8, gives me a mean absolute deviation of 4.5. My mean absolute deviation is 4.5 for this data. This is a much more efficient way of calculating mean absolute deviation than the way I did the first example, because making this new column, even though it's really wide with the skinny numbers in it, looks a bit silly, making this new column allowed me to get all the data I need, and I didn't forget to count the data point that happens to be equal to the mean, and that doesn't even always happen. You don't always have a data point that's exactly the size of your mean. That's just a coincidence when it happens. But when it happens, the difference between them is 0, and that 0 has to be included. Adding a 0 doesn't change this total. The 0 has to be included because we have to divide by 8 and not make the mistake I almost made, dividing by 7 in the previous example. How am I doing for time? Very little time left, so what I can do is I can find mean absolute deviation from one more data set. So I'll choose a nice small data set from one of the previous examples from today so that I can finish it quickly. So remember, when you're finding mean absolute deviation, you can say to yourself, I'm mean and I'm mad. And saying I'm mean reminds you, start by finding the mean. Okay, let's just take, here's a weird bunch of data. Why not use some weird looking data? That data I had 3, 17, 82, 84, 88, 905. Need another comma. More useful to put it in a column. There are how many of them? There are 6, so we're going to divide by 6. Let's get the calculator so I can do it faster and hopefully not make a mistake. 3 plus 17 plus 82 plus 84 plus 88 plus 905. What kind of value is that? 1,179 divided by 6 gives me a mean of 196.5. That's my mean. Hard for me to write down here on the bottom of the chalkboard wall. Now my mean absolute deviation, I need to add the deviations, the difference between 196.5 and 3. Whew, 193.5. Difference between 196.5 and 17. I thought this was going to be a simple one when I chose this little group of data. It's not so simple. I'm using my calculator. I don't want to make a mistake. 196.5 minus 17. 179.5. I wouldn't have chosen this example if I had thought ahead. 196.5 minus 82. 114.5. Seems horrible, but actually it's not so bad. Fortunately, there is only 6 data points. 196.5 minus 84, 112.5. And I bet some of the students are doing this in their head faster than I'm doing it with the calculator, but I just want to be careful. 196.5 minus 88 is 108.5. All of these are smaller than 196.5. Now I'm in trouble. I'm about to do 196.5 minus 905. No, bigger number first. 905 minus 196.5. 708.5. Okay, I didn't leave room at the bottom to show the total, so what I'll do is I'll show the total. And again, I don't want to make a mistake. Ran out of chalk. Now I'm down to holding a little tiny stub of chalk in my hands. Okay, the total, 708.5. I'm going to clear this. 708.5 plus 108.5 plus 112.5 plus 114.5 plus 179.5 plus 193.5 equals 1417. And when I divide that by how many values I had, which is 6, divided by 6, 236.2. That's a bit of rounding. 236.2. So why did we get such a huge mean absolute deviation? That's why. These bunch of smallish numbers and that huge number, that's going to put you in a position where you get a very big mean absolute deviation. It's a measure of variability. It's the correct measure of variability. I hope I didn't make a mistake. You guys let me know if I did. I am out of time, so I'm going to wrap this up now. We can use a few more examples of mean absolute deviation. It's a bit of a long process, but notice how it involves using the mean that we learned last week, and finding means is something that we have to get good at and get used to doing. Means and medians keep on being so useful. Okay, so the measures of variability. Range, pretty fast to find usually. Interquartile range, a little bit more work, involves the medians. And then mean absolute deviation, also a little bit more work and involves the means. They're all measures of variability. They're all measures of how far the data deviates from that central value which we call the mean. And from myself and my beautiful assistant who's upstairs, I would like to say goodbye for this week. And I look forward to next week when we are going to get into some graphy type stuff, and that is part of the fun of statistics, is when you make it visual. Have a nice week, and goodbye.